So the idea behind these worksheets is you're figuring out a whole bunch of stuff about GPS and how relativity applies to GPS. So one of the things they're having you do is calculate how much energy it takes to get a satellite into orbit. So a lot of this stuff is a review of Physics 1. So we have each GPS satellite launched from the Earth's surface by rocket. How much work must you do to get the rocket up there? Work has a lot of different definitions. The one they gave you on this sheet is work. Let's get the right colors. Work is equal to force times the distance that you move it. There's other definitions of work, though. Work is also equal to the change in potential energy. So you're changing this rocket's potential energy when you're moving it from being on Earth to in orbit. So what you want to do to find the work is you calculate the potential energy when you're in orbit, and you subtract off the potential energy when you're on the surface of the Earth, because that's the difference in energy you're applying on this. Okay. So we have an equation for potential energy. They give it as E sub G. It's going to be equal to negative big G times M times little m, all divided by R of your orbit, minus a negative G times M over R when you're on Earth. So then the next step is to plug and chug your numbers in. What numbers do you plug in? For G, what do you plug in? 6.67, the constant that they give you. So they give you that number. So we can write this out as negative 6.67 times 10 to the negative 11. For big M, so this is the gravitational potential energy between two objects. The two objects are going to be Earth, going to be big M, and the rocket that you're launching is going to be your little one. Right? So big M is the mass of Earth, which was given as 5.97 times 10 to the 24. And little m is the mass of the rocket. Oh, do they give you the mass of the rocket? If you read problem 2, do they have the mass of the rocket in there? No. If you read problem 1, do they give you the mass of the satellite rocket? Yes. So each of these questions, they build on the stuff in the previous question. So you can get constants that you need in the previous part. So the mass of the rocket they give you is 2 times 10 to the third. And then we divide this by the radius of the orbit. So that's how high up this satellite goes. Did they give us that in this question, in question 2?
It's in question 1.
It's in question 1. So we have each satellite orbits at this distance from Earth, 2.66 times 10 to the 7. Okay. So, yes?
Where would we have found the alternate definition for work? Just in the textbook somewhere? Or?
In the textbook and from doing Physics 1.
Okay.
Prior knowledge.
Gotcha. Okay.
The other place you could find this on all these worksheets, and I usually save this for the end of class, but there's solutions for all of these at the end of that whole packet. So all the answers are already there. And it gives you this equation. So we have this work equation. That is the work that you have when you're in orbit, and we want to subtract off the work that we start with when we're on the Earth surface. So we still have the mass of the Earth times G times the mass of the satellite. And this time we want to divide by the radius of the Earth because we're sitting on the Earth's surface. So what's the radius of the Earth? Did they give us that number? Yeah, what is it?
6.37 times 10 to the 6 meters.
6.37 times 10 to the 6 meters. So then you'll plug and chug all those numbers in, and you'll end up with your final answer of 9.5 times 10 to the 10 joules. Okay. You could do it with work equals force times change in position, but you have to plug in the right force equation and the right change in position equations. The right force that you have going on here is the force due to gravity, but it's not on the surface of the Earth, so you can't just use F equals mg, because it's not on Earth's surface, right? So we have to use the more general equation, F is equal to g m1 m2 over r squared. The universal law of gravity, you can plug that in and plug in the distance that you're traveling, and you could get the same answer. It's just easier to get the answer with the energy. Okay? Any questions on that one? No? So now the really cool one, I like this one. We'll do question number 4 on that worksheet number 3. So somebody read that question 4 for me. Extra points.
Einstein's theory of special relativity and general relativity and opposing effects on time in the GPS. Einstein's theory of special relativity states that the clocks inside GPS satellites run slower than a stationary clock on Earth by 8.3 times 10 to the negative 11 seconds per second. This is due to the speed of the satellites. Einstein's theory of general relativity says the satellite clocks also run faster than those on Earth by 5.2 times 10 to the negative 10 seconds per second, because Earth's gravity is weaker at the satellite's altitude. And then part A is how much slower does a GPS clock run each day due to special relativity? How much faster does it run each day due to general relativity?
Okay. So this is cool just because you kind of see the effects. These are very small changes, right? We know special relativity does things to time. What is speed due to time in special relativity? The faster you go, what happens to your clock? Clock slows down. That happens on GPS satellites. It happens that every second that ticks by, your clock runs 8.3 times 10 to the negative 11 seconds slower per second of time. Okay. And part A in this wants you to figure out how much that corresponds to for a whole day. So to figure that out, to figure out these time errors, in part A, the total time error due to special relativity, I'll call it delta T SR, is equal to the time error, 8.3 times 10 to the negative 11 seconds per second. And if I want to get that time error over the course of a day, I'd multiply that by the number of seconds in a day. And then it'll stack up all the little uncertainties. So how many seconds are in a day? Oh, goodness. Can we figure that out? There's lots of ways to do it. Somebody figure it out. Connor's calculating.
86,400.
86,400 seconds. How do you get that number?
It's 24 times 60 times 60.
24 hours in a day. 1 hour is 60 minutes. And 1 minute is 60 seconds. So do this nice little factor label. The hours cancel, the minutes cancel. 24 times 60 times 60, 86,400. So you plug and chug all those numbers in, and we get an answer. Let me scroll down and see what that answer is. (8.3 times 10 to the negative 11 times 86,400. So what numbers do you guys get? Go ahead and plug it into your calculators. Make sure you can type these numbers in.
Uh, 7.17 times 10 to the negative 6.
7.17 times 10 to the negative 6 seconds. Okay. Does that seem like a big uncertainty in time? Doesn't seem like a big effect, does it? No. Okay. And let's check the uncertainty due to general relativity. So how would I find that? Any ideas? Uncertainty in time due to general relativity.
Wouldn't it be just the same thing with a different number?
Same thing with a different number. So general relativity is 5.2 times 10 to the negative 10 seconds per second. Multiply that by 86,400 seconds. And that gives us a change in time due to general relativity. That's equal to, I think we got 4.49 times 10 to the negative 5 seconds. Which uncertainty is bigger? Which one has a bigger effect? Special relativity or general relativity? Look at them very closely. Which one's bigger? General relativity or special relativity? Talk about each tables. Tell me which one's bigger. When you have your answer, look at me as though you're the most bored person in existence. You're all very good at that. I don't know. General relativity? I disagree. 7.17 is bigger than 4.49. Exponents. Yeah. Minus 5 is bigger than minus 6. So general relativity is a bigger effect. So that's the bigger effect on these things. You all got it right. Yay. Okay, part B. Somebody read part B for me. Part B.
GPS satellites signals at the speed of light c. Any timing error in the GPS translates into a distance error equal to distance equals c times delta time error. Calculate the daily distance error for the special error.
Okay, so they tell us how to do it. You take the errors from part A, multiply it by the speed of light, because that's how fast the signal's traveling. That gives you your distance error. So let's see what these distance errors are. Special relativity. I do my 7.17 times 10 to the negative 6. Multiply that by 3 times 10 to the 8th meters per second. And I get a distance error of 2151 meters. Do the same thing for general relativity. My time error of 4.49 times 10 to the negative 5. Multiply that by 3 times 10 to the 8th. I get a distance error of 13,470 meters. And part C. What do we do for part C? What does it say? It says to calculate the difference between these two distances to find the overall distance error per day from relativity. So all you have to do is subtract one from the other. So I'm going to do 13,470 minus 2151. That gives me 11,319 meters. Is that a big number? Is that a lot of meters? What distances do we usually use in the United States? How do we measure distance? Miles. So let's convert that to miles and see how many miles it is. So if your GPS didn't use special relativity and general relativity to correct itself, let's see how far off you'd be after a day. You can just type it into Google, that's fine. 11,319 meters. How many? 7 miles. Without relativity, your GPS would be off by 7 miles in the span of a day. That's pretty bad, isn't it? Yeah. So it's good that we have these inclusions. So I'm going to do one more problem. I want to do worksheet 4, and I want to show you problem number 2. Okay? You should be able to do all the other problems, but there's one important thing that we need to point out in problem number 2. So somebody do me read problem number 2 for me. Actually, don't worry about it. Special relativity, they give you this relationship, the time dilation equation. Right? And then they tell you that GPS move as satellites, move at a specific speed, specific velocity. GPS satellites move at a velocity of 3.874 times 10 to the third meters per second. And that's much less than the speed of light. So you can use the relativity equation, you can kind of change it so that it looks like this. Delta t prime equals delta t times 1 plus v squared over 2 times c squared. So that's approximately the same result that you get from the time dilation equation. The reason we do this is because it helps calculators handle it better with rounding. If you use the time dilation equation, calculators don't really carry enough digits to round well, so you end up with the wrong answer. So this approximation will get you to the right answer actually easier. Okay? So what they ask you to do in part A is calculate what is v squared over 2c squared. How would I do that? How do I find v squared over 2c squared? Do I know what v is?
What are you trying to solve for, the whole thing? Or
Yeah, they just want us to calculate what is v squared divided by 2c squared. Can I plug in the digits? Do I know what v is? Yeah, what's v?
3.8.
3.874 times 10 to the third. And I square that. Divided by 2c squared. What's c? Speed of light, 3 times 10 to the 8th. Plug this into your calculator and tell me what you get. This is important to plug into your calculator. Make sure you can get it. Make sure you can get these numbers. If you're going to screw up on an exam, it's going to be a calculator error.
I got 6.75 times 10 to the 24.
Nope. That's not what I got.
You're probably right.
Maybe I did it wrong. I am in a haze of Mucinex. Mucinex induced stupor. What did you get? 337 times 10 to the negative 11. Anybody else get that one? Yeah. 8.337 times 10 to the negative 11. So you should keep doing that calculation. Make sure that you get that number so that you know how to put this into a calculator. If you put a parentheses in the wrong place or it rounds weird, you want to make sure you're getting that number. 8.337 or 8.34 times 10 to the negative 11. If you're more than that, off by more than that, then you recalculate. These questions are a little tricky in that if you're not putting it in just right, you will get the wrong answer. And it'll screw up subsequent parts. So that's part A. And then part B asks you how large or how slowly does someone on Earth see a GPS satellite running over the course of a day? Okay. So how do I find that? How slowly a clock runs over the course of a day. They gave us this equation, delta t prime equals delta t times 1 plus v squared over 2c squared. What you could do is that delta t prime, and they tell you this in the problem itself, delta t prime is a clock on Earth. Delta t is a clock on the satellite. They want to know what happens, what kind of time do you read in a clock on Earth if you let the clock on the satellite run for 24 hours? How many seconds of difference do you get? So how would I do that? First, what variable am I solving for? Do I want delta t prime, the time on Earth, or do I want delta t, the time on the satellite? Again, let's read the question again. How slowly does someone on Earth see a GPS satellite running over the course of a day? So we want the person on Earth, the person on satellite. Earth. So we want to get delta t prime. Yep. So we want to calculate this. So I need something to plug in for delta t, something to plug in for 1. That one's easy. And v squared over 2c squared, we just found what happens. What do I plug in for delta t on the satellite? How much time is going by on the satellite over the course of a day? How long is a day? How many seconds? We just found it. Look back. Just a little bit. 86,400. Okay, so delta t prime equals 86,400 times 1 plus 8.34 times 10 to the negative 11. Plug that into your calculator and tell me what you get. Times the whole quantity, 1 plus 8.34 times 10 to the negative 11. Parentheses. Should get 86,400. 0.00000072. Make sure when you plug it in your calculator, it's rounding to that many digits. If it's not getting you that, raise your hand. What is it getting you? Is it just giving you 86,400?
Minus 0.00001.
So it's getting you out to this number of digits. Okay. Is that true for everybody? Yours is.
I'm just getting 86,400.
Yeah. What calculators do you all have? 84 plus. That one's not. Is that even a calculator? You steal it from a museum? Yeah, nope. Okay. Do me a favor, how many of you have laptops? You have laptops? So type this into Google. Let Google do it for you. type it into Google, do you get 86,400.000000072?
Yeah.
Yeah. Okay, so Google carries out the right number of digits. Your calculators seem to not. Your calculators seem to round. For those of you that got 86,400, did you do it all in one step, or did you do it in multiple steps?
One step.
So when I do it in one step, I get 0.00001. Okay. So the reason we did this is so that I could test your calculators and see what you're getting, so I can design the exam so that you get the right answers. Okay. So that helps me. You should be getting this number. So using this number, how slow is my clock on Earth? Yeah, 0.0000072. 7.2 times 10 to the minus 6 seconds. Okay. So we're clear on what that means. So if I gave you this problem and you got your answer, and I told you that this was how slow it was, you would know how to calculate the amount of time. You subtract the day off of this. Yeah, that's pretty clear. Any other questions on any of this GPS stuff? You should finish off that worksheet 4, make sure you know how to do that. And then next class, I think we move on to the next chapter. Yeah. Everybody have a good weekend. Enjoy the snow. And you should get an email from me this weekend if you asked about doing prosthetic legs. We're going to get people started on that kind of work.